Good morning, students, and welcome to this final exam review video. The final exam has 40 questions, out of which 25 questions are conceptual, and the remaining 15 are calculations. Remember that the final exam is only based on chapters that you have after exam 3, which would include temperature and heat, transmission of heat, kinetic theory, heat and thermodynamics, and then you have oscillations, waves, and sound. So those are the chapters. Now watch this video very carefully, take notes, and try to understand. The focus must be on understanding, not on memorization. I am directly speaking about the questions on the final exam. So this should be the time that you have set apart and you are really focused as you listen to this video and you try to do your very best on the final exam. Thank you and wish you the best. All right, the first topic is oscillations. So what you see here in this diagram is actually a spring with a mass at one end and the other end fixed. So when you pull the mass down and let it oscillate, it's going to go down to B, if you pull it down to B, and then go all the way back up to C and then to A, and then it'll continue the oscillations. So here the question is, at what position is it moving fastest? For sure, it's at C. So that means when the mass is moving from A to C, it's speeding up. It is the fastest at C, and then as it goes to B, it slows down until it stops at B and turns back. So that's what is happening. That means the potential energy is maximum at the two positions A and B, because that's where the spring is either maximum compressed or maximum extended. So the potential energy is maximum at A and B, while the kinetic energy is maximum at C. So that is the first concept. All right. Number 2, we know sound is produced by vibrating objects, but we can't hear all vibrations. We cannot hear anything less than 20 hertz, neither can we hear anything more than 20,000 hertz. So the human hearing is between 20 hertz and 20,000 hertz. Anything less than 20 hertz, which we cannot hear, are called infrasonics, and all frequencies above 20,000 hertz, which is really useful in the medical field, are called ultrasonics. That is concept number 2. You have surely heard about ultrasound, which is used in medical imaging. All right, so number 3, the kinetic theory of gases. So here we talk about moving molecules that have kinetic energy, and of course we know that the higher the temperature, the faster the movement, or the higher the velocity. So on the left-hand side, what you see is kinetic energy, and this line here just shows mean velocity of the molecules, because not all molecules are moving at the same velocity. So the left-hand side is the mean kinetic energy, the average kinetic energy. On the right side, N shows the number of degrees of freedom. Degrees of freedom. For a monoatomic gas like helium, it has 3 degrees of freedom. For diatomic gases like oxygen, nitrogen, there are 5 degrees of freedom. For polyatomic, that means anything more than 2 molecules like Carbon dioxide has 3 molecules, 1 of carbon, 2 of oxygen, 3 atoms, I must say, 3 atoms. So for all polyatomic gases, there are 6 degrees of freedom. So 3 for monoatomic, 5 for diatomic, 6 degrees of freedom for polyatomic. So that's N. 1/2 kBT is the energy of a molecule. Now T is the temperature in Kelvin. Kb is a constant which is called Boltzmann constant. So that's not very important here. What's important here is to know that the average kinetic energy is proportional to the temperature, which means if the temperature increases, then the average kinetic energy also increases. If the temperature doubles, the average kinetic energy also doubles. All right, but when you try to make velocity the subject, you see you have a square root there. So I have simplified it to this. So when average velocity is the subject of the formula, you have to remember there is a square root here. So which means if the temperature quadruples, means it becomes 4 times. Square root of 4 is 2. That's when the velocity doubles. Okay, so keep that in mind. So next, you have to know the meaning of specific heat. Specific heat is the heat required to increase the temperature of 1 kilogram. 1 kilogram of any substance through 1 degree Celsius. So you want to heat 1 kilogram of any substance through 1 degree Celsius. That's the amount of heat that you have to give it. So that's specific heat. The specific heat of water is very high. It's 4,186 joules per kilogram per Celsius or per Kelvin, okay? It's very high. And because the specific heat of water is very high, you could even jump into a lake in summer or a swimming pool in summer and the water would not be so hot. Because the specific heat of water is high, the rise in temperature of lakes, swimming pools, and oceans is very, very small. So that is what you have to understand. You also have to realize that the coolant used in automobiles is basically water with antifreeze added, of course. And it's possible to use water as a coolant because water is capable of absorbing a lot of heat with a small rise in temperature. So that is the next concept. Moving on, we come to thermodynamic processes. So when we talk about thermodynamic processes, there are basically 4 types of processes. Isothermal means temperature is constant, because iso stands for constant. Isothermal, temperature constant. Isovolumetric, volume constant. Isobaric, BARIC, pressure constant. And then adiabatic. The name is slightly different. Adiabatic means entropy is constant. So there are 4 processes because there are 4 thermodynamic variables. Okay, once again, temperature constant, isothermal. Pressure constant, isobaric. Volume constant, isovolumetric. Entropy constant, adiabatic. Now, you should be able to recognize these processes from the graphs. So, you see a pressure-volume graph, pressure on the y-axis and volume on the x. And if you see a graph like this, like number 1, you know that the volume is increasing, but the pressure is constant. But if you look at number 2, the pressure is increasing, the volume is constant. So number 1 is isobaric, number 2 is isovolumetric. But down below you have a temperature volume graph. So you got to be careful. That's temperature on the y-axis, which means number 3 shows what? Increasing volume but constant temperature. What's number 4 showing? Well, decreasing volume but temperature constant. Right? Make sense? Now go to number 5. Look at number 5. This graph shows that the volume is increasing, the pressure is decreasing because it's going down. Look, the pressure is going down. So it's from here, the pressure is high, here the pressure is low. So increasing volume, decreasing pressure, but the temperature is constant. Oh, now we can't make it out, but we know if the volume is increasing and the pressure decreasing, it has to be at constant temperature, so that's isothermal. Okay, so that's what you have to know from there. Now, in all these processes, you can have change in internal energy, so that's delta U, that is change in internal energy. Means what? Change in temperature. So when a gas absorbs heat, when a gas is heated, its temperature goes up. That means its internal energy goes up. But at the same time, the gas is able to expand and do work. So it uses a part of the incoming heat, to increase its internal energy, and uses the remaining part to do work for expansion. If you add up both of those, you get the quantity of heat coming in. Isn't that simple? So if 100 joules of heat is coming in and 70 joules is used to increase the internal energy, 30 joules is used to do work, because 70 plus 30 is 100. So you have to know what these terms stand for. Now, by definition of an adiabatic process, this is where the system is completely isolated from its surroundings, so no heat can come in and no heat can go out. So Q is 0 for an adiabatic process. Now, what about if it's an isothermal process? Then the temperature does not change, isothermal. If the temperature does not change, then the internal energy does not change. That means change in internal energy is 0. I hope you're paying attention. Isovolumetric means what? No change in volume. That means the gas is not expanding and neither is it contracting. So it cannot do work. So that is another concept that you have to know on the exam. Now, staying on the track of work, whenever gas does work, you can find the work done by finding the area of the pressure volume diagram. So here you have 1, 2, 3, 4 processes. This is just like in a Carnot's engine, if you know what that is. That's where we got the word car from, C-A-R. That's the name of a scientist, Carnot, C-A-R-N-O-T. So there are 4 processes. That's an expansion. That's another expansion. So this is isothermal expansion. This is adiabatic expansion. Isothermal compression and adiabatic compression. Okay. So this is called a cyclic or cyclic process because it comes back to where it started from. And to find the total work done, all you have to do is find the area of the diagram. Find the area of the diagram. Well, entropy. Now, you only have to learn a simple formula about entropy, and that is change in entropy is heat entering or leaving the system divided by the temperature. And there is one specific case that you have to know. That is change of phase, like melting of ice into water or freezing of water into ice. Now, when ice changes into water, when it melts, it has to get heat. So it takes in the heat. And when it takes in the heat, the entropy goes up. On the other hand, when you freeze water to make it ice, you are removing heat, aren't you? When you remove heat, the entropy decreases. So just remember, whenever heat enters the system, entropy increases. When heat leaves the system, entropy decreases. And we can calculate the change in entropy because we know that in change of phase, the formula used is mass times latent heat. So first calculate that. For example, if the mass of water being changed into, or ice being changed into water is 1 kilogram, and this is the latent heat of ice, just multiply those two, you get dq, and then you know that the freezing point of water or the melting point of ice, same thing, is 0 degrees Celsius, which is 273 Kelvin, right? You have to always have it in Kelvin. So when you plug it into this formula, this is what you get. See that? 3.33 times 10 to the power 5 divided by 273 gives 220. And the unit is, of course, a joule on top and Kelvin below. So the unit is joule per Kelvin. So that's how you work that out. So that's about change in entropy. I also want to tell you that during an adiabatic process, you remember what an adiabatic process is? The system is completely isolated. No heat can come in, no heat can leave. That means there is no change in entropy. I'm telling you. In an adiabatic process, there is no change in entropy. Did you write that down? Okay. Now, moving on to a Carnot's engine. In a Carnot's engine, you got to look at that, look at Carnot's engine, Carnot cycle, understand its working. There you know that heat is first taken in by the working substance. That is called QH. Heat absorbed by the working substance is QH. And then it converts a part of it into work. And then whatever remains, whatever heat remains, it rejects. That is QC. So I told you QH is the heat taken in, QC is the heat given out. And the work done is the difference between the two. And efficiency is work over QH. Okay? Usually efficiency is expressed as a percentage, in which case you would have to multiply this formula with 100. Not just that, every formula down under with 100. So that's a basic definition of efficiency. But there's another formula in terms of temperatures. Again, write it down. Temperature has to be in Kelvin. So efficiency can also be calculated using this formula, where you have the temperature of the hot reservoir and then minus temperature of the cold divided by the temperature of the hot. Now, when it comes to refrigerators, you know refrigerators are heat engines working in the reverse cycle. We don't call it the efficiency, but we call it the coefficient of performance. I know, so many terms. Coefficient of performance of a refrigerator is given by this formula. See that? So the refrigerator is actually taking heat from the food inside and throwing it out. So see, that's where your QH comes in. Heat being removed. That's divided by the work done. But when you talk about a heat pump, which is what we use to keep our homes warm in winter, there the the formula is QC over work. So notice a change. See that? If you look at this, for a refrigerator it's exactly reversed, but for a heat pump it's not reversed. It's reversed and QH is replaced by QC. I hope you got that. Then you have adiabatic processes where to calculate, entropy is constant, so pressure, volume, and temperature, all three change. And so there are two formulas at least I want you to know. One is pressure, volume raised to gamma is a constant. Now you're like, what's this? That's Greek gamma. Yes, you got to learn Greek too. By this time you realize gamma is called the ratio of specific heats. So the story is that gases have two specific heats. One is specific heat at constant pressure. The other is specific heat at constant volume. And the top one is always bigger than the bottom, so the ratio turns out to be more than 1. And for monoatomic gases, it's 1.67. For diatomic, it's 1.4. For polyatomic, it's 1.33. I'm talking about the values of gamma. Anyways, you got to remember that if it's an adiabatic process, this is the formula used. But if it's isothermal, then look at the change. Look at the process. The formula has no gamma. What does that mean? That means in an isothermal process, if you increase the pressure 2 times, like you take a gas and compress it, you increase the pressure 2 times, then of course the volume becomes half, doesn't it? Like, because you're compressing it. But that's not the same for adiabatic process, because there is this gamma coming in, see? So you got to be aware of that. Now, what do you mean by latent heat? Latent heat is the amount of heat required to change 1 kilogram of ice into water, or 1 kilogram of water into steam. So latent heat is where there is a change of phase. So also remember that once water begins to boil, this is important. Once water begins to boil at 100 degrees Celsius, which is 373 Kelvin. Once water begins to boil, you can continue heating it, but its temperature is not going to change. Did somebody write that down? You can heat it with a stronger stove. All that you will be doing is changing water into steam faster. The temperature is not going to change once the change of phase begins. Okay. Next topic is the transmission of heat. Please read on this. There are 3 ways: conduction, convection, and radiation. Conduction takes place in solids and is given by this formula. So here there is a problem that I'm asking you to work out using this formula. So Q is the quantity of heat, T is time in seconds, K is a constant for the material, because we know that the heat conducted depends on the material. So K is the constant called thermal conductivity. A is the area of cross-section. So if it's a rod, you're only looking at the cross-sectional area, okay? You're not looking at the whole surface area. TH and TC are the temperatures of the hot end and the cold end. So if you have one end of a steel rod, for example, in a furnace, and the other end is out in the open, you see TH is the temperature of the furnace and TC would be the temperature of the room. And D is the length of the rod. Now it could be the thickness of a window pane. Like a window pane, for example, in summer the temperature on the outside of the window is higher, that's TH. Temperature on the inside is TC. That's the room temperature. Okay, and then in that case the thickness of the window would be D. There is a question based on conduction. There's also a question based on calorie. Calorie is another unit for heat. It's a practical unit. We don't use that so much in physics, but you got to know it's a much bigger unit than joule. How do we know? Because 1 calorie is 4.186 joules. See? Just 1 calorie is equal to 4.186 joules. That means joule is smaller. You need more joules to equal 1 calorie. And what is 1 calorie? If you take 1 gram of water, 1 gram, that's small, and you want to heat it through 1 degree Celsius, you have to give it 1 calorie. That is a calorie, okay? Just know the definition of a calorie. And then you have this question, if you take a disk with a hole in it and heat it, what happens to the size of the hole? Well, it increases. So you see that the hole in the middle of that metal disc increases. And to find the change, this is the formula you use. There is one problem based on this formula. It's important to know that in this formula, delta L is the change in length. Well, in this case, it would be the change in the radius. Okay? So this would be for heating a rod. And L would be the original length. Delta T would be the change in temperature. So you're heating it from an initial temperature to a final. So that's a change. Alpha is a constant called linear expansivity. Linear expansivity. That'll be given to you. So if you're given these three, you just have to multiply them to find the change in length. But if you're asked to find the new length, what do? Then you have to first find the change in length and then add it to the original length. Right? Did you write that down? So if you're asked to find the new length, you can't just find the change in length and leave it at that. Okay? Now, I think this concept, I did talk about it earlier, so I'm not going to talk about it again, but that's important. Remember that the temperature is proportional to the square of the velocity. That's all I'm saying. Avogadro number. What is Avogadro number? Most students are able to give me the number. They'll go 6.022 times 10 to the power 23. That's good. But what is it? It is the number of molecules in 1 mole of any substance. Number of molecules in 1 mole of any substance. So you take 1 mole of oxygen, or you take 1 mole of carbon dioxide, or 1 mole of anything, they will have the same number of molecules. That is the Avogadro number. Very important to know that. 1 mole of any substance has the same number of molecules. Well, you got to know how to change from Celsius to Fahrenheit and Fahrenheit to Celsius. I'm not giving you the formulas here, but you got to know. You also need to know that Kelvin is the temperature scale that we have to use. If you use Kelvin all the time, you're never going to make a mistake. And the important thing about the Kelvin scale is that you do not have any negative temperatures on the Kelvin scale. Because the lowest temperature in the Kelvin scale is 0 Kelvin. It's called the absolute zero. You can't have negative temperatures on the Kelvin scale. And also good knowing that on the Celsius and the Fahrenheit scales, negative 40 Celsius is the same as negative 40 Fahrenheit. When you put it into the conversion formula, you will get that. Okay, so that's all I had for you, students. And thank you for all the hard work that you've done during these 8 weeks. Doing physics in 8 weeks is a challenge. You've taken it up, and some of you are doing really, really good in this class. So give it the best shot you can for the final exam. And I just wish you the very best. Thank you.